record.
Yes. Okay.
That's well. So thank you to all of you for being here. We have now the second talk of the day by Gabriel Barrenechea. He got his mathematical engineering degree from Universidad de Concepción in Chile in 1996. Then he moved to Paris to get his PhD from the University Paris Dauphine in France. And then he came back to Chile to hold a professor position at Universidad de Concepción until 2007. And at that date, he moved to Scotland, okay, to start a position in the University of Strathclyde, where he currently is a reader, okay. Gabriel's research is in numerical analysis of PDEs with a strong focus on finite element methods for fluid mechanics. Well, he's a very active member of the community in numerical analysis. He has been very kind and open to help new generation of researchers and has many collaborators from South America and other countries. So for me, it's a great pleasure to introduce Gabriel to all of you. Please, Gabriel, go ahead.
Thank you. Thank you very much. Can you all hear me okay?
Yeah, it's very well.
Great. So first off, thank you for the invite. It's a great pleasure to give this talk in this very nice initiative indeed, and of course to a wider South American community that, for obvious reasons, is very nice. So I appreciate the invite, Eduardo, and all of you. I thank everyone for being here. So I'm gonna talk today about something that has been my main focus of research for the last few years, and it's about possibility preserving discretisations. So essentially, it's a little bit, I'm going to tell you, part of my work on trying to propose finite element methods that preserve a very important property of partial differential equations, and that is the maximum principle. And so this work is, of course, not work done in isolation. This particular work is done in collaboration with several people. My main collaborator is probably Tristan Pryor from the University of Bath, but I've also, today I'm going to talk about works with Manolis Georgoulis from Harvard Watt, Andreas Wieser from Milano, and of course Abdulreza Hamidi from the University of Strathclyde. He's actually at the moment finishing his PhD under my supervision. And I'm going to, I know it's a 40-minute talk, so and I know I'm a little bit outside the PDE area that I guess that most of you are specialists in partial differential equations. So I'm going to spend quite a lot of time actually introducing and motivating a little bit what I'm doing. And then the heart of the talk, or kind of the main cause of the talk, is going to be this new method that we have introduced over the last few years. And then I'm going to give a couple of extensions that probably I'm going to cut one of them appropriately at the end if I have time restrictions. So essentially, I'm going to spend most of my time introducing the topic and presenting the main idea of the method. So I'm going to start with a motivation. I'm going to start with a couple of equations where we need to respect bounds, where we actually need to we need discretisations that respect certain bounds of the solution. So the first one is the Allan-Kahn equations. So the Allan-Kahn equation is a partial differential equation. It's a reaction diffusion. By the way, V should be U, so apologies for the typo. That's a particular personal best of having a typo on the first page of the presentation, actually. So this is a reaction diffusion, nonlinear reaction diffusion equation that appears in phase field models. And it's a nonlinear reaction diffusion. And at the continuous level, at the PDE level, what happens is that the solution belongs to -1, 1. The solution to a partial differential equation belongs to -1, 1. And if the numerical method that if our favorite numerical discretization for this equation does not respect these bounds, then there is a blow up in the simulations. especially because this nonlinear reaction term gets excited by this very small parameter epsilon that leads to an exponential growth in errors. So actually, if your favorite finite difference, finite volume, finite element method, whatever you're doing, does not give you solutions between -1 and 1, you're going to end up with blow up in finite time. And that actually, you can write small code and convince yourselves of that fact. Another example that is very, very close to my heart in terms of applications is variable density flow. As Eduardo mentioned, my research has been a lot around fluid mechanics. And in this case, this is an example where we look for a velocity u and a pressure p of an incompressible fluid, right, that occupies a domain omega. And the key, this is not just Navier-Stokes. The key point is the fact that our density is variable. And there are thousands of examples where density is variable. I mean, temperature-dependent flows, multi-phase flows, free surface flows. You have countless examples where you have actually variable density flows. And the main issue is that the density is driven by this transport equation. And of course, the density cannot be negative. As a matter of fact, the density cannot even be zero. If the density is zero, you don't have a fluid. So the model loses physical sense in there, and of course, mathematical sense. So we need to propose a discretization that preserves the positivity of the density in this case. Also, for purely stability reasons, linked to the fact that the density appears multiplying the viscosity of the flow. So if the density goes negative, the viscosity goes negative, and the problem becomes unstable. So essentially, there's a lot of, there are several reasons why you really, really want to keep the density positive on this. And that there has been a lot of work in these two particular examples on different methods that guarantee positivity or non-negativity of solutions. So these are just two examples that help us understand, or I hope that convince you that actually presenting discretizations that respect the positivity of the solution actually is worth doing. Right. So from a mathematical point of view, the fact that rho is positive or that u belongs to -1, 1 actually are particular cases or extensions of what we know in partial differential equations very well as the maximum principle, right? So one of the first qualitative properties of elliptic partial differential equations such as this one, which is a second-order diffusion convection reaction equation here, is that if the right-hand side is positive, then the solution is positive, of course, and under certain conditions, it's not only the solution remains positive, but the solution has no interior minima. So there is no a change in concavity of the solution as well. Now, that result that you learn in your first class in theoretical PDs in university does not transfer to 99% of the numerical methods. As a matter of fact, if you take your off-the-shelf finite element method and you just write your standard conforming find a discrete u in the space of piecewise linears. I'm just going to focus on linears, but it doesn't really matter actually. Piecewise linear elements with strongly imposed boundary conditions such that the finite element system is satisfied. The same condition does not hold, the same result does not hold unless the mesh satisfies extremely restrictive conditions. So what are these conditions? The mesh needs to be strictly acute. And what I mean by this is that you have a triangulation of your domain. Every angle needs to be strictly acute, not even weakly acute. Strictly acute the minute that beta is there, the minute there is convection, right? That's one thing. And very refined. Now, you can think, okay, so I will just build a strictly acute mesh. point of the matter is that in two space dimensions, building strictly acute meshes is doable, is possible. In 3D, it's extremely challenging. And there are some even more complications that actually, if you're interested in high-dimensional PDEs, this is impossible to begin with. Any PDE for dimension, any domain for dimension higher than 5 can be proven that an acute triangulation is impossible. That's one aspect. But even in 2 and 3 space dimensions, it's extremely challenging. That's one thing. And the second thing I wanted to mention is the second component, very refined aspect of this problem. What do I mean by very refined? I mean that this mesh width needs to be proportional to the diffusion coefficient. And typically in problems for example, linked to fluid dynamics, this epsilon value is much smaller than the rest of the coefficients. So typical values for epsilon, not that small, are 10 to the minus 3, for example. And what we need is that the mesh width, so the size of your elements, is of the size of epsilon. So in 3 space dimensions, your mesh would require 1 divided by epsilon cube elements, which can be, we're talking about 10 to the 9, 10 to the 12, if epsilon is moderate. So these two are really, really very restricted conditions to satisfy what we call the discrete maximum principle. That is, given a positive source, getting a positive or zero solution. So, and this is of course not new. This has been around. People realized this in the 1970s, mostly the work by Philippe Ciarlet and collaborators mostly Philippe Ciarlet himself actually, who took the work in M matrices coming from Varga and then translated into computational partial differential equations. And it became very, very clear very soon that whatever method we need to propose to satisfy this property at the discrete level needs to make the diffusion bigger. So if you take a look at the matrix associated to this finite element method, this matrix behaves badly, this matrix behaves very badly, while this is the only one that behaves well. So to actually propose a discretization that satisfies the discrete maximum principle, what we need to reinforce the Laplacian. But the issue is that it's not just go and reinforce the Laplacian and essentially add a large number and approximate your PDE, because that means adding way too much diffusion. So what the finite element community did was to actually steal ideas, or borrow ideas from the finite volume community and go to shock capturing type schemes or discontinuity capturing methods, which are nonlinear methods that come in a tremendous amount of flavors, colors, and shapes, and which I like to actually just present as in one very idealized nonlinear way, which is essentially take your finite element method, right, and add a Laplacian to the equation, but a Laplacian that is numerical and it's not linear. It depends on the solution itself. So essentially, how do these methods work? They go through every element of the triangulation and they build a switch that switches on whenever you need diffusion in that element. If you need diffusion in that element, it switches on. If you don't, it switches off. And these switches, of course, depend on the solution itself. So you go from our standard finite element method in the previous slide to this finite element method, we go from linear to nonlinear. But that's absolutely fine, because every discretization that respects bounds is nonlinear to begin with. So that's not really the issue. So they go from linear to nonlinear. And what they are designed for is they're designed to actually suppress the extrema. So they go element per element looking for extrema, local extrema, maxima, minima, and when they find one, they switch on the diffusion and they flatten the solution. And this is what they do. And they go element per element, and they actually, there is a very, very, very big, very long history of these methods. As a matter of fact, together with Volker John from Weierstrass and Peter Knobloch from Charles University, we wrote this very long review paper last year, telling a little bit the story of methods, in particular finite element methods that respect the discrete maximum principle. The emphasis was convection diffusion equations, but essentially second order elliptic and parabolic equations. And we told that story, and we were a little bit not frustrated, but there were a lot of untold stories. So we decided to release a much longer version of that work, and we just released this book that is going to be available for download in a couple of weeks in Springer Verlag. That is called Monotone Discretisations of Elliptic Second Order PDEs, where we did finite elements, finite volumes, and finite differences methods, but with an emphasis on finite element methods for second order partial differential equations. And it sounds a little bit like we wrote a book just in the one method, but it's essentially all the family of methods that can be seen as something that looks like this very Lego version discretization, nonlinear discretization I was talking to you. So this is this book actually covers what I like to call the systematic way of respecting the discrete maximum principle, which is proposing a nonlinear discretization for a second order PDE. Now, not everyone actually does sit down and write a new discretization. Many people, what they could do is that they go back to the application, for example, the Sovian and Can, and they advance in time. They realize that they went beyond 1 and they went under -1. What they just do is just cut the solution and move on in time. Same thing with variable density. Your density is negative, it doesn't matter. You put it to a minimum density and you move on. Many people just do that. So you can do this process also in a cutoff version. You just can go cheap and dirty and just chop the solution, right? And this is something that many people actually use. There are many finite element codes that take this approach, and it's actually a decent idea. Well, for certain problems, you can actually prove that it works. As a matter of fact, there is a really nice paper by Christian Kreuzer that probably 10 years ago now, or a little bit longer, he sat down, wrote just a symmetric problem, a reaction diffusion equation with constant coefficients, and proved that actually just chopping the solution works. And by works, he meant the error you commit is bounded by the standard finite element. Okay, but that is good news. But this alternative actually is not really satisfactory for several reasons. First of all, the minute you chop a function, it's no longer a finite element function, because you essentially go in the middle of an element. If you cross 0, then you essentially are getting a piecewise polynomial function inside the elements. So it's really hard to prove stability when you don't have an object which is the result of your simulation that is not in the finite element space. So this is one counter. This is just a post-processing. This chopping process is just a post-processing. So you don't have a discrete problem that you're satisfying. You just compute, you solve your finite elements problem, and you chop the solution, and that's what you get. This is just a post-processing. You cannot write an equation. And of course, the arguments that Christian Kreuzer gave to prove these results were arguments based on energy. So he was actually very much focusing on symmetric problems. The minute you introduce non-symmetry, non-self-adjointness, actually the whole argument goes out the window. So this is the situation we were when we started working. It usually takes me, it takes me 15 minutes to start actually talking about my own work here. So we have this situation where you have a very systematic way of proposing a shock capturing type method, which works really well, but the analysis is only done for low order. I'm not going to go into dwell too much on those details. Or on the other hand, you have this chopping strategy that is very cheap. So it's very practical. It's very, very cheap, can be implemented extremely easily, but it has its own problems. So this is where we were sitting a few years ago, and we decided, you know what, we're going to try to propose a method that writes an equation for something that looks like this. It's not like this, but it looks like this. And I'm going to try to explain this in the next 20 minutes. This is how essentially we came to what we end up calling a nodally bound preserving method. So I'm going to set ideas. I'm going to talk about just a reaction diffusion equation. So these are reaction matrix, so symmetric, positive, definite. I'm going to suppose that it's strictly positive definite. So this is a properly elliptic equation. This is my weak formulation that we all know and love by now. And I'm going to make one fundamental assumption. And this fundamental assumption is that U respects bounds. And I know those numbers. That U is in a given interval. For example, for Alan Kant, it was between -1 and 1. For the variable density equation is essentially the density is bounded below by a fixed constant. But you can think of thousands of equations where we actually know the bounds. You know that concentrations need to be between 0 and 1, for example. You know that probability density functions need to be between 0 and 1. So essentially, it can be a strong hypothesis to assume that I know both bounds, but there is a tremendous amount of applications where this is actually achievable. Okay? Okay, so this is my main framework, my partial differential equation, and I know that the solution satisfies certain bounds, and I know those bounds. So what do? I build a shape-regular triangulation, standard, any shape-regular simplicial partition, can be quadrilateral as well, it doesn't matter. And I build my standard finite element space of continuous functions, piecewise polynomials of degree, whatever, k, and I impose the boundary condition strongly, and of that space, I build this set. This is a closed convex set of all the finite element functions, not that they respect the bounds at every point, but that respect the bounds at every node of the triangulation, right? So I can and this is just a closed convex set, a closed convex subset of my finite element space. Of course, it's not a subspace, it's a closed convex subset. And when I have a finite element space and a subset, I can split every finite element function into its positive part and the negative part. I call them positive and negative. It's not really right, but essentially it's whatever is in the closed convex and whatever lies outside. Okay? Right. So I'm building up. So how do I build the method? I start with my favorite finite element method. So essentially for reaction diffusion, just to fix ideas, I'm going to start with my standard off-the-shelf finite element method for this problem that you teach your students in, I don't know, 4th year, 5th year university. And my unknown is the finite element solution. But what I want is, I don't want a problem for UH, I want a problem for the part that is inside the convex. So what I do is I write the equation for UH plus, not for UH. Sorry, I just saw something that popped up in the chat actually. Right. So there is where was I? Apologies. So I start with my standard finite element method. I want my problem for the UH plus. I can write that problem except for the fact that when I go from this point to that point, I introduced a kernel, because this plus operator maps everything that is negative to 0. So going from, I not only I made my problem nonlinear, but actually I introduced a kernel into my formulation. So what do you do when you introduce a kernel? You introduce some stabilization to remove the kernel. So essentially I went from the standard finite element method to a problem that seeks the positive part of the solution, and it adds a stabilization to remove the resulting singularity. So this stabilization, we discussed several ways of stabilizing. We require this stabilization to be strong enough so it removes the singularity in a stable way, so it respects the stability of the underlying partial differential equation. And the stabilization we came up with was this mass lumping type stabilization. It's extremely simple to implement in the finite element context. This is just adding a diagonal matrix to your finite element code, and it has some weighting factors to make it equivalent to the energy norm. And this is our method. Our method is essentially, you take your finite element method, you write the exact finite element method, but for the plus. That introduces a kernel, so you design a stabilization that compensates for the kernel, and that's the method. So you look for a finite element function, which is not the standard finite element function, whose positive part and negative parts satisfy this variational equality. So this stabilization has several advantages. It's extremely simple to implement, as I said before, but it also, very importantly, it's compatible with the plus and the minus. It respects the hierarchies that the plus operator and the minus operator gave you. In other words, what I'm saying is that it leads to a monotone operator. So,
Hola, Gabriel.
oh, hola, Norman.
¿Cómo estás? ¿Puedo preguntar durante tu charla?
Of course, yeah.
Sorry, I'm speaking. So is it trivial that there exists a solution in your subset, in your convex subset? You talked about the kernel, but the existence is trivial?
Of what? I mean, the subset is not empty. That's one thing. So if what you mean is that...
Yeah, I did not completely understand. You just replaced UH by UH plus. So that's a post-processing step, or you're just looking for UH plus in the subset of this convex subset, and that exists.
Okay, so that is the point. So this is not a post-processing step. I'm looking for UH plus in the convex, and I will prove in 5 minutes that this has a solution.
Okay, fine. Thanks.
Yeah, that's the point. Yeah. So yeah, so that's the right way of putting it actually. So as I was saying, this stabilization here, what it does, it's essentially it induces a monotone operator, and what we're doing is essentially A is an elliptic bilinear form. I'm adding something that is monotone. So at the end, this nonlinear scheme that I proposed is linked to induces a strongly monotone and continuous operator. So the discrete problem has a unique solution. So this, a little bit to answer Norbert's question actually, this nonlinear scheme, I can prove that it has a unique solution in the full finite element space. Its plus part belongs to the convex set, and the minus part is whatever is outside the convex set. Now, I could take a look at this scheme and just analyze it like that, and it works. But there is something much more interesting about this scheme. than that, actually. And I'm going to go through this a little bit fast, but the key point is that doing some manipulations, which I'm not going to detail too much, we realized that by picking test functions carefully and by going through the motions, and very importantly, by using the monotonicity of the partial different of the stabilization method, what happens is that for the solution to the discrete problem, the constraint part, this plus part, satisfies this variational inequality. So I'm going to repeat it. I'm going to repeat the variational inequality here. If you take a look at this variational inequality, then you realize that this means that this approximation in the convex is the orthogonal projection of the exact solution in that convex. So then proving error estimates for this is trivial because it's just the definition of the orthogonal projection. So what we're doing, what in a really strange way, is we went through a very, very long process to rediscover the orthogonal projection onto the admissible set of solutions, right? And that's quite neat because it closes the circle from that perspective. And you could say, okay, so you don't need to talk about stabilization, you don't need to talk about your numerical method, you just solve directly the variational inequality as a control problem, as a constraint control problem, and you get your solution. That is very true. But this gives us a much more general setting that we can use for problems where the interpretation of as an orthogonal projection does not follow through, actually. And this is what I'm going to try to explain in the next probably 10-15 minutes. Right. So let me summarize. You have your partial differential equation. You know your convex set of admissible solutions. You put a plus in your finite element method. You add a stabilization. If your problem is symmetric, you end up with the orthogonal projection. So we solve this problem, and we solve this problem for several different cases, all of them in meshes that look like this. Why is this mesh interesting? This mesh is interesting because we have obtuse angles. So for this mesh, it is proven that the solution of a second-order elliptic PDE will not preserve positivity. The numerical solution, pardon me. Right? So essentially, and despite the fact that we have meshes that have obtuse angles, we still have solutions that belong, of course, by construction to the acceptable admissible set, and that converge optimally to the right, with the right rates. And also, and this is something that is fairly neat, is a nonlinear discretization, but it's very cheap. So it's not an expensive nonlinear iterative. It's not an expensive variational inequality to solve. It's fairly straightforward. We can also, of course, approximate problems with very sharp interior layers or boundary layers. So we can solve this problem with a very similarly perturbed epsilon is 10 to minus 7 here. Your standard Galerkin solution would have, your standard finite element solution would have massive, huge under and overshoots, while the solution, our constraint solution, is actually fairly good looking. We kill the undershoots, of course, by construction, because this is the UH plus, which is by definition built to belong to this interval 0-1. But also we kill the undershoots, but we kill the resulting overshoots as well. If you are familiar with these sort of problems, what you typically get is that when you get an undershoot, you get a rebound of an overshoot. You get massive oscillations that you go very negative, very positive, very negative, and then you get dumping after a while. In this case, we actually kill the undershoots and the overshoots at the same time. Sorry. And we have also used extend this to more general setups. And this is what I was telling you, why it's important to actually build this as take your finite element method, but put the plus at stabilization, because that interpretation for orthogonal projections and variational inequalities stop making so much sense when you end up with nonlinear reaction terms, for example, as in this case. So we're able to expand this to a nonlinear reaction, a problem with nonlinear reaction. We still have well-postness because the nonlinear reaction here is monotone. And we also have optimal order error estimates with respect to quasi-norms, right? Not the standard norms. We need a quasi-norm because of this nonlinear reaction term here. And this is the problem we chose. We chose a problem with anisotropic diffusion, a fairly anisotropic with very small diffusion, and a nonlinear reaction. On the left is the problem, is the solution to the standard finite element method. On the right is the solution, is the plus version, is our constraint solution. They don't look too dissimilar in the eyeball norm if you look at this, but when you look at it a little bit more carefully, and you take the ISO values, you realize that away from this obstacle where the solution is said to be big, you get these wiggles. Essentially, the solution goes really negative and then comes back up positive, negative, positive, negative, positive. And you get these wiggles as you get away from this obstacle, while the solution kills, as I said, it doesn't go negative by construction, but it doesn't go positive either. It's monotone away from the layer. So it respects the behavior of the method, of the actual solution to the reaction diffusion equation I was talking. So that is essentially the main idea of the method. I'm going to spend the next 5 minutes talking about two quick applications to it, but I want to insist on the methodology. So I'm going to the difference between the reaction diffusion equation I was discussing earlier and the convection diffusion equation is, of course, this first order term that it becomes really interesting when this first order term dominates. This is the weak formulation. Essentially, the natural space is H10, of course, and this is the bilinear form A. And the key point is, again, do your favorite finite element method that you have, put a plus in the discrete solution, constrain it to the acceptable set, and then add a stabilization that removes the kernel you introduced by that setup. There is a caveat with convection diffusion, is that the favorite discretization we want is not the plain Galerkin, but we want some sort of stabilized discretization. We want to add some linear stabilization to compensate for the fact that we're very, very convection dominated. I'm not going to dwell too much on this. I don't want to get too technical, but the stabilization we chose here was continuous interior penalty. So it's essentially, we added a Laplacian, but a linear one. And the stabilization now needs to compensate. It's the same stabilization as before, but with an extra term that actually takes into consideration the fact that we need to compensate for the kernel we introduced in the convective term as well. Now, the structure of the discretization is exactly the same. You had your standard finite element method, you put a plus in the solution, that introduced a kernel, we added stabilization. The issue is that this convective term, this non-symmetric term here, prevents us from being strongly monotone again. So existence of solution well-postness becomes a lot more challenging. So what we had to do was we had to do something a little bit more convoluted. We went through fixed point arguments. So we essentially, what we did was we stood up on what I presented 10 minutes ago. We sent to the right-hand side everything that has to do with convection. And we used Brauer's fixed point theorem to prove that there exists a solution. Then we did the exact same process of proving that for any solution, the constraint part, the positive part, satisfies a variational inequality. This variational inequality is uniquely solvable thanks to Span-Packet theorem. And then, since for every single solution to a nonlinear scheme, the positive part satisfies a variational inequality, then actually, and that variational inequality has a unique solution, then we can prove that the problem has a unique solution. In general, of course, we no longer have the property that our UH plus is the orthogonal projection because the problem is non-symmetric, so we don't have the best approximation property, but we can actually prove optimal convergence using different techniques. We had to work a little bit more and we really had to work a little bit more on the error estimates here, but things follow without much of a problem. So again, I'm using meshes to present a few numerical experiments. I'm using meshes for which the angles are obtuse, so the discrete maximum principle is not satisfied in this case for standard discretisations, and we get solutions. We tackled problems that look like this, which is essentially we have a steps shape profile that we are propagating to the interior of the domain. So we have essentially transport where we start with a steps shape and we propagate that discontinuity inside the domain, and we get solutions that lack any significant type of oscillation. We did a cross-section here, and this is for quadratic elements, and we see that we get the solution is pretty much 0 here and pretty much 1 here and pretty much 1/2 in the middle, and the numerical solution respects that. Very interestingly, we see that the orange one is our bound preserving method that remains between 0 and 1, while different at this pure CIP discretization, the linear standard finite element solution goes above 1 and of course below 0. I'm so sorry. I'm just going to mention very quickly that we have extended this to many different cases, but I'm just going to talk about the time-dependent case. Philosophically speaking, it's the exact same thing. We assume that the solution is bounded by two different numbers. The upper bound is of course depending on time now. And what we do is that we take the standard discretization and we take the evolution of the positive part, and the stabilization, of course, now needs to compensate for the fact that we are solving a time-dependent problem. So philosophically speaking, as I mentioned, it's the same thing. You take your discretization of the partial differential equation, your standard finite element method, you write the same equation for the plus part, and you add a stabilization that controls the kernel. We can prove in the time-dependent scheme, in the time-dependent setup, we can prove existence, uniqueness of solutions, stability, and error estimates. And just to wrap up, I'm going to show you one particular numerical experiment, which is this three-body rotation problem by Levesque, that essentially we get an initial configuration and we rotate it. So essentially we subject this to a circular convective field, and after one rotation we compare the initial condition to the final configuration, and this is the results that we get when we use a low order time discretization implicit Euler, and this is when we get a second order time discretization, and we see that the bound preserving solutions remain between 0 and 1 as we wanted. And for quadratic elements and Crank-Nicholson time-dependent discretisations, actually the diffusion, this is a cross-section around this area, and this is fairly difficult to actually not get extremely diffusive profiles, and the profile is fairly decent. So, yes, I think I should stop talking actually. So what have I presented? This is inexpensive. This is a cheap way to hardwire bounds in the finite element solution. This is not a post-processing. This is a way in which we write a finite element method for a solution that we know that belongs to the already by construction to an acceptable set of solutions. That process gave us the orthogonal projection into that set for linear symmetric problems. But the advantage of the approach is that the strategy is general enough, so essentially extending it to different partial differential equations, in particular convection-dominated problems. Polyhedral meshes, I didn't talk about that now, but we're actually finishing the paper now on polyhedral meshes. But we have extended this to nonlinear PDEs. We have extended this to, for example, not us, but a group in France extended this exact method to the Allen-Kahn equation. So this is a fairly generic strategy, a fairly easier to understand strategy as well. And actually, there are many, many open questions, most of them theoretical. But what I really, really want to do is I want to apply this to hyperbolic conservation laws and to obtain, to be able to prove convergence to entropy solutions using this approach. And on that note, I think I'm going to stop talking and thank you for your attention.
Thank you very much, Gabriel. Very nice talk. So now it's a time for questions. So please, Jefferson, just open your mic and ask your question, please.
Hi. Thanks, Gabriel, for the talk. I have a question. In the item 3, for example, in PD's problems, can be considered this strategy in discrete or semi-discrete?
What time-dependent problem you mean?
For example, convection diffusion.
Yes.
Yeah. In the PDE, in this case, is a problem in evolution. Okay.
Yes.
Okay. The same strategy is possible in semi-discrete or discrete.
It's so what I wrote here is for the fully discrete problem.
Yeah.
But
Okay.
essentially, if you think about this, if you replace this by the time derivative of the positive part, you're
Okay.
tracking the evolution of the positive part of the solution, right? So philosophically speaking, Jefferson, what we do is that we approximate the PDE written for the positive part.
Yeah. Okay.
Whichever approximation you use is for the PDE written for the positive part, and then so it's extremely flexible in terms of what discretization we're using.
Yeah. I have a question because I don't see results in discrete case. Discrete the time and the space.
Good. So this is discrete space and time actually here.
Yes. Only not the space.
What do you mean? Can you rephrase that? I'm not sure I'm understanding actually.
For example, usually
Yes.
one discretize the space in this case, but in PDE problem one can discretize in time
Yes.
in both parameters.
Yeah. So the issue. Yeah. So I mean, for this approach, for essentially for what I'm saying to make sense, you really require a space discretization somewhere.
Yeah.
Because otherwise, if you discretize only in time, if I'm understanding it
Yeah.
correctly, essentially the conservation or the positivity preservation comes as a consequence of the PDEs that you get for each time step.
Okay.
So that,
Right.
I mean, the conflict happens with space discretization.
Okay. Good. Nice. Thanks, Gabriel. Thank you for
Thank
the
you,
talk.
Jefferson. Yeah.
Thank you, Jefferson. Thomas, please.
Hi, Gabriel. How are you?
Hi.
I have a question. So you showed that you basically your method, right, delivers the metric projection
Yes.
on the so you get to the best approximation within the restricted set, right?
Yes.
And so before you showed the result of Kreutzer.
Yes.
So I didn't get it completely. So he proved that when he just cuts off, right, then he gets basically the best approximation, right? If I understood correctly.
Yeah, that's exactly it. So Christian, what he did is he took a reaction diffusion equation with constant coefficients, and what he said is that defining this object, which is your standard chopping, you get your oscillating, you chop it at 0 and 1, and he computed that the energy of this guy is smaller than the energy of the finite element solution.
Yeah, which is the best approximation.
And that's the point. So it's better.
So
That's exactly what happened.
yeah. So, but in your case, it's like it's a little bit weaker, right? Because you cannot prove that this.
Oh, no, of course not. Yeah.
That your, let's say, solution is the best approximation also in the global finite element space, or equivalent or something.
Agree.
So, and my question is, so did you have a look at the case? So he cuts off in all points, right? In all on the interior point, and you're just imposing conditions on the node, right?
Yes.
So you're could you just basically take the finite element solution from a standard finite element method and just impose this condition also in the node and as a post-processing? Then you would get the finite element function, right? And
so that's it. That's a possibility. One could do that. It has some inconveniences and some inconvenience, and one of the issues is conservation. Because you have these over and undershoots, that these high oscillations, you kill if you're going below 0, you kill the negative points, but the rebound oscillation stays there. So you push everything up. So you're not conservative. We're not conservative, but we are very close to being conservative. So you lose that a little bit. And to me, actually, from a mathematical point of view, it's very important for me to actually have a discrete problem. Doing any post-processing, you cannot write an equation for the post-processed quantity. Do you know what I mean? And this is what we wanted. We really wanted to have a finite element problem for the object we were chasing. That's why, yeah. I don't know if I'm making sense.
No, I understand. Yeah, but yeah. So, but I mean, at least like say so in this situation, the lowest order case, I mean, it would be sufficient to make this problem, right? To take the approach from Kreutzer, right? So because in the linear case, I can nodally impose the conditions and I have the.
You're good. Yeah.
Okay. And then I know it's more or less the best approximation. Okay.
Yeah.
Now I understand. Okay. Yeah, I get it. Yeah. Now for higher order makes sense. Yeah, true. Okay. Thanks.
No worries.
Thank you, Thomas. Maybe there are some other questions. Norbert, please.
Yeah, if there's still time. So if I understand correctly, Gabriel, in numerical experiments, in some cases, the discretization strictly satisfied the bounds, and in some cases it did not. Or is that correct?
So So let me go here. Let me go to a convection. So,
And is the influence easy to see on what it depends, if I've seen it correctly?
so for example, this case, so this is plane Galerkin to the left. So this is a problem with anisotropic diffusion.
Yeah.
Essentially, you set the solution to be 2 in the obstacle and 0 on the outflow, not outflow, outside. And what happens is that these sharp profiles here, the plane Galerkin discretization actually goes negative in these regions here, right?
Yeah, no, I've seen that. I think that is perfect in your case. Yeah.
Yeah. Now, for convection diffusion, this case is fairly illuminating. So essentially, we did a cross-section here. What we compared, the green curve here, is a linear discretization of this same problem. This is convection diffusion with quadratic
Yeah.
elements.
It's your method or standard finite elements?
This is standard. It's standard plus continuous integral penalty.
Oh, yeah.
So it's essentially a stabilized discretization. It's standard plus a little bit of numerical diffusion, right?
Okay.
So this is a linear method, not guaranteed to satisfy the discrete maximum principle. So you have these violations. It goes above 1.
Sure.
While our method stays below 1 by construction.
So I just cannot, it's not so clear on the image whether on the lower part, whether this orange curve goes into negative region or not. So that was not so clear.
Well, this is an interesting point. We are guaranteed not to go negative. We're guaranteed not to go negative at the nodes.
Okay.
What happens in between the nodes is open, but we are yet to see a case where we actually go negative in between the nodes.
Okay.
I cannot explain that. I cannot prove it.
Yeah.
But
No, it's fine. I just want to see the results again because I was not, so of course, just a short talk. I was not so clear what the theoretical results are and what is just numerics.
No, but that's an interesting point actually, and this is something that we're very, very curious about.
Yeah,
One of the
sure.
reasons why we want to do local analysis
Mhm.
is to see what actually happens in between the nodes.
Yeah. Yeah, very interesting.
Thank you.
Thank you, Norbert. Maybe there are some last questions to Gabriel, no? Well, if not, well, I have just a short question. Many times on the talk, there are the norm of the operator D, no, of 0, infinity, omega I,
Yeah.
on slide 13.
Yeah.
What is that there? What's there? Yeah, can you give us some insight or?
Something like this, you mean?
Yeah.
Yeah. So we don't need to compute that. So we presented the method in practice. If you know D, you could just replace that by the maximum value of D in the whole domain, and you're happy. So this is you don't need to go element per element computing these norms. That's what I'm trying to say.
Okay.
Unless you have a nonlinear problem and that's a different kettle of fish, then you need to do something different. But these guys, you can just approximate them by either the value at the nodes, or you can approximate them, but just overkill and just use the infinity norm on the whole domain of D. If it's data, you just compute the maximum value. Yeah.
Okay.
And that is enough to implement the method, yes.
Thank you, Gabriel. Well, thank you very much for this very nice talk and very nice results. To all of you, Lorena and Gabriel, thank you for these wonderful talks today. And just to end this session, so just I wanna say that the next session of this seminar is on March 19. Okay, we will have Noemi Volansky from Argentina and Raúl Quintero from Colombia. And today's talk will be available on our YouTube channel next Sunday. Okay, so thank you very much again to all of you for being here. Bye-bye.
Thank you.
Bye.
See you soon. Bye.
See you.
In the winter.
Yeah.